Yes, Sasrikal students, let's derive Bernoulli's theorem. Very important theorem, which is very, very important in understanding fluid flow. Well, here, let's take this tube with two ends, end A and end B. Obviously, as you can see, this tube is having varying cross-section area, and we are imagining a steady fluid without any turbulence. This fluid is flowing. If there is an obstruction, so there are some eddies formation. So that is not there. It's a steady flow. Also, we are having assumptions that the fluid is incompressible, means its density is not changing. Its density is constant as the fluid is flowing from end A of the pipe to end B. The density is not changing. We are not able to press the fluid, or there is no expansion or pressing in the fluid. It is incompressible, and we also imagine that the fluid is irrotational, as I have already told you. When I say irrotational, obviously it means the fluid is steady. So these are the streamlines of the fluid, and no streamlines are crossing each other. Okay, and then we also uh, assume that the fluid is non-viscous, means the viscosity is not there, that we will study later on. The fluid is imagined to be made up of so many layers, hundreds and thousands of layers, and these all layers actually they move relative to each other. The velocities of every layer is different. Now, in case it's a tube, students, actually the layer of the fluid which is near to the tube always flows with least velocity, and the fluid layer which is at the center, it always flows with the maximum velocity. So because of that velocity gradient, there is a friction between the fluid layers. So that we are imagining it's not there. It's a non-viscous fluid. So we are imagining that the velocity at every point is constant, which is actually not the case. This fluid streamline actually will have the maximum velocity, but we are imagining it's not the case. Okay, it's a non-viscous fluid. And why we are imagining all this? Just to simplify the calculations and just to have understanding. Whenever we talk about science or mathematics, thermodynamics, anything, first we do assumptions and talk about and postulate something ideal, and then we compare other things with that ideal thing. So then we are able to understand everything. Okay, so these are the assumptions. Okay, in mathematics also we do a lot of assumptions. Okay, so students, already we have seen P1 is the pressure of the fluid at cross section A, and P2 is the pressure. Here you something important. This There is a pump here actually. There is a pump here which is thrusting this fluid inside. See, fluid is going up. It will go up only if there is a pressure of the fluid, right? For example, let's see, there is a fluid contained in this tank. So fluid will flow here because there is a pressure of the fluid because of this height, that is equal to rho g h. So pressure of the fluid here is very less, right? It increases with the height. So that's why that pressure is imparted by the pump. Or maybe there can be a big container. Imagine that there can be a big container, and in that container we attach the tube. Automatically there will be pressure created here because of this height, and the fluid will flow like that. Anything you can imagine. This is the pressure. So this pressure we are imparting to the fluid, right? This is the pressure. And at point B, you know P2 is the pressure. Okay, so let's go now. H1 is the mean height of the fluid, at A, and H2 is the mean height of the fluid at B. V1, V2 are the velocities of the you know fluid at section A and B. All right. So students, obviously you can understand that P1 is greater than P2, then only the fluid will flow. And in that case, V1 would be greater than V2 because of the pressure. The this velocity would be more, and we can say that this velocity is less. You know, right? So, but then, as we have imagined that mm, we have imagined that this cross-sectional area is more and this cross-sectional area is less. So I think this will be wrong. We have to imagine that V2 is more than V1. Okay? Well, it is right, students. If the pressure at this point is more, obviously fluid particles will flow at greater velocities. In case it has same cross-sectional area, then at a distance the velocities will decrease, and that's what it came to my mind. But I forgot that we are not taking a very big tube, we're taking a small section of the tube. And since the area here is bigger and area here is smaller, so according to equation of continuity, a1 v1 is equal to a2 v2. So obviously v2 will be more than v1. So sorry for the mistake, huh? Okay, fine. So v2 would be more than v1. All right. So having stated that, this is according to continuity theorem, continuity equation, or whatever you say. Fine. So now, students, mm, you see what is the force on the liquid at section A. So that is pressure is forced by area. So the force on the liquid at section A would be P1A1. Am I right? So this is the force which is thrusting the liquid inside. So what is the work done on the liquid? Students, see, this is very important. We are doing the work on the liquid. Work done on the liquid. Who has done the work? The pump has done the work. Or as I told you, this is an imaginary container. So because of that potential of water, that edge of the water, the pressure is imparted. So we are doing the work on the liquid. Work done on the liquid, at cross sectional A. So that would be equal to P1 A1. This is the force. Am I right? Force multiplied by distance is the work done. But here we will take work done per second. So work done per second means there will be joule per second. So that then easily we can multiply it by V1. Important thing you will understand, because in V1 we have meter per second. So P1 A1 is force Newton into meter per second. Newton into meter would be joule. So this is joule per second. Work done per second. That's why I wrote work done per second on the liquid, right? Okay, so this is done. And now, mm, work done by the liquid. This is the here it's not work done on the liquid, it's work done by the liquid. Now the liquid is doing work, here we have done the work. So work done by the liquid we are taking as negative, right? So it would be P2 A2 V2. Okay, so students, in thermodynamics is totally opposite. Work done by the gas, work done by the gas in a chamber is positive, and work done on the gas when we move the piston is taken as negative. In thermodynamics it's reverse, but in fluid dynamics, uh, it's opposite. We are doing work on the liquid is positive, the liquid is doing work, so we take it as negative. So it will be negative P2 A2 V2. Am I right? Now this can be equal to, you see, A1 V1. A1 V1 is volume per second. So we can write P1 V1, right? So similarly, we can write this at minus P2 V2. V1 V2 are the volumes, right? Volumes of fluid elements. Okay. So what is the net work done per second? You see, we're talking about net work done per second on the fluid because of pressure energy. This work is done because of pressure energy, right? So that is equal to P1 V1 work done per second. See, I've already included per second. Why? Because here it was volume per second. P1 V1 minus P2 V2. All right. Now, see students, mass m of the liquid flows, per second from A to B. Mass m, mass m. Some books you will have m dot mentioning it is mass flow rate. Okay, but m is mass. Its unit will be kg. When I take mass flow rate, its units will be kg per second. In some books you will have mass flow rate. It doesn't matter because here everywhere we are imagining mass per second, work done per second. All right. So we are compensating for that. So students, the height is increasing from h1 to h2. Am I right? So we can say change in potential energy as a fluid is moving from section A to section B, change in potential energy. In your book, Pradeep, it is written increase in potential energy. That is right. But then he's also writing increase in kinetic energy. Okay. So instead of that, we can write change in potential energy. Okay. So students, change in potential energy is, mg H2 minus H1. I think you can understand this. Potential energy is mgh. So similarly, change in kinetic energy. So that I can write as half m v2 square minus v1 square. All right, students, again, because uh, it is we've taken everything as per second. So this is potential energy per second. Am I right? Potential energy, increase in potential energy per second. So similarly, change in kinetic energy per second, half m v2 square minus v1 square. All right. Now, you see, this change in potential energy and change in kinetic energy happened because of what? Because of the work done, net work done in moving the fluid from A to B. So that means work energy principle, we will say this change and this change happened because of this net work done. So we can easily write what P1 V1 minus P2 V2. This is the net work done. Well, that is giving rise to change in potential energy mg h2 minus h1 plus change in kinetic energy. Obviously, everything is per second. Half m. So it will be v2 square minus v1 square. You please rearrange the terms. When you rearrange the terms, you are getting this, students. P1 V1, okay, V1 and V2 we can equate to V. Why? Because we have assumed that it is an incompressible fluid, so mass flow rate or volume flow rate is not changing. So we can write this is V also, P1 V, right, plus m g h1 plus half mv1 square minus terms on this side is equal to P2 V plus m g h2 plus, yes, anyone, plus half m v2 square. Now students, you simply divide the whole equation by m. What will you get? You will get P1V P1V by m. Simply divide all the equation by m plus GH1 plus half mv1 square would be equal to P2V by m plus GH2 plus half V2 square. I've just divided everything by 1. I see that, students, density is equal to mass by volume. So mass by volume ulta. So this will be P1 by rho. P1 by rho. right? See, mass by volume नीचे से P1 by rho plus GH1 plus half V1 square can be equated to P2 by rho. Can anyone help me complete this? Plus GH2 plus half V2 square. Am I right? So what does it mean? That means P1 by rho plus GH1 plus half V1 square. This is, because of pressure. This is because of the potential. This is because of the kinetic component. So this all these three components, either you can say of fluid, or you can say of a fluid particle, or you can say of a fluid element. Okay, fluid element, or you can say any fluid particle, or these three energies possessed by the entire fluid, doesn't matter. So is same as, the sum constant of all these three at point B. So that means this is a constant. See, these P1 by rho, GH1, half V1 square. These are the components of energies because of pressure, potential, and velocity. This is same, So you see, P1 by rho and P2 by rho, these two can be different. GH1, GH2 obviously are different because H2 is greater than H1. Half V1 square, half V2 square is different. But sum total of all these three, sum total of all these three is equal to this thing. What does that mean? This is constant. Very interesting. This is constant. That is Bernoulli's theorem. So we can write it like this: P by rho is pressure energy per unit mass. Pressure energy per unit mass plus GH. See, potential energy is mgh. So what will be GH? Potential energy per unit mass plus kinetic energy is half mv square. So what will be half v square? That is kinetic energy. Yes, Ishma. What is half v square? It will be kinetic energy per unit mass. Divide this by m, you will get half mv square. Am I right? So let me wrap this. And gh plus half v square is equal to a constant. This is the derivation of our Bernoulli theorem. Okay. Well, students, this can be written as in the other ways also. How? Now, how can we state this? The sum of pressure energy, potential energy, kinetic energy per unit mass is constant at all the cross sectionals of the streamline flow of an ideal fluid. Okay, that is Bernoulli's theorem. Okay, so students, I've written, just see again, I'll write P by rho plus GH plus half V square is equal to constant. Okay, now let me multiply everything by rho. What is that? That is the density of the fluid. So I'll get P plus rho GH plus half rho V square is equal to constant, right? This is, student, this is other form of, this other form of Bernoulli theorem. All right. All right, students. And now I get to the crux. I'm sorry, this is, yeah, P plus rho GH plus half rho V square is equal to constant. Okay. Now this equation, when I divide by G, let's see what I get. I divide by G. P by rho G, this form of equation mostly used in our engineering purposes, plus divided by G. So it will be H plus half, or we can say V square by 2G is equal to constant. This is most widely form of Bernoulli theorem used worldwide So students, this is known as pressure head. This is known as what? Gravitational head or potential head. And this is known as kinetic head or velocity head or dynamic head. Kinetic head. Why they are known as heads? This is other way to represent the fluid energy in terms of meter. See P by rho g. See P is equal to rho g h. So when I divide P by rho g, I will get only h. Its unit is meter. Am I right? Meter. Pressure energy in terms of meter. H obviously is in meter. V square by 2g. V square is m by meter by second. So meter square by second square divided by meter per second square. See that? Meter square by meter, that is again meter. So its unit is also meter. Students, as the units of these pressure energies, uh, potential energies, and kinetic energies I've expressed in terms of meter in fluid dynamics or in fluid mechanics, these energies are known as pressure head, gravitational head, kinetic head. And see that dimensional homogeneity of this equation we have already proven, because you see all these terms, they have the same units, that is meter. So students, this is again another form of Bernoulli equations. All right, now comes the limitations of Bernoulli's equations. So students, you see that number one, we have assumed a steady flow. It's not always steady flow. Number two, we have assumed that the velocities, the density of the fluid is not changing, which is not the case. Number three, we have assumed that the velocities of every streamline is same, but actually I've told you, in a tube of circular tube, this center one particle will move with a maximum velocity, because of the things we'll explain you later. As you go up, the velocity decreases. As you go up, the velocity decreases, and this layer of the fluid, which is in touch with the internal layer of the tube, this layer of the circular layer of tube, which is in touch with the internal, cross-sectional area of the pipe, is not moving at all. Well, this is no slip condition. No slip condition. So in other videos, these things will be clear to you. So students, with this, I take leave. Uh, to revise it, if there's any doubt, please write in the comment section. Don't forget to subscribe the channel. Thank you very much.